Hello, and welcome to this very brief presentation on integration using partial fractions with repeated linear factors. This presentation does build on previous presentations, particularly the integration using partial fractions with linear factors, and it's strongly recommended you view that presentation before reviewing this presentation. Here's a brief overview of the underpinning topics and techniques we'll be using within this presentation. You need to understand partial fractions, integration using standard forms from standard tables, integration using the substitution method for non-standard forms. The cover-up rule will be used to find the constants in the partial fractions, and the equating coefficients method will also be used to find the constants. For your reference, there's another presentation relating to partial fractions, and within that the use of the cover-up rule and the equating coefficients method. There's a separate presentation on integration using standard forms and integration using substitution. As within the previous presentation, there are some conditions we need to be aware of when we're undertaking our partial fraction calculations. Two checks as we term them. The first one is that the numerator should be at least 1 degree less than the denominator. In the example on the right hand side, the 4x minus 5 in the numerator is 1 degree less than the x squared minus x minus 2 term in the denominator. And also we endeavour to factorise the denominator. So in other words, an expression such as x squared minus x minus 2, we would factorise into x minus 2 and x plus 1 in brackets. Those two checks we will undertake within the solutions we will review on the following slides. And here again are our three types of partial fraction. In the previous presentation we considered linear factors. Now in this presentation we're going to consider repeated linear factors. What we will find now is we have a function of x in the numerator divided by an x plus a term that's raised to a power of say 2, 3, 4, etc. So for this particular form of a repeated linear factor, the partial fractions would be constant a over the x plus a plus the constant b over x plus a squared plus the constant c over x plus a cubed. If this had been a squared term here, we would have just had the two partial fractions shown here. And for reference here, we've got the table of standard integrals that we used in the previous presentation. Example 2. We're asked to determine the integral of 3x plus 7 divided by x minus 1 all squared with respect to x. Undertaking our checks, we can clearly see the numerator is lower degree than the denominator in this case, because the numerator is basically x to the 1. Don't forget there's a 1 here that we do not write. And the denominator is an x squared. If we expand the brackets, this would be an x squared term. Obviously we can see that the denominator is factorised. X minus 1 multiplied by x minus 1 is x minus 1 squared. So this is obviously a repeated linear factor. We have a squared term outside of the bracket. So 3x plus 7 all divided by x minus 1 all squared can be written in partial fraction form as constant a over x minus 1 plus constant b over x minus 1 all squared. Initially in this presentation I'm just going to review the partial fraction technique, and then we will review the integration process later. All that's changed on the next line is that I've written the right hand side all over the common denominator of x minus 1 squared. Notice I must multiply the a by the x minus 1 to ensure that I haven't changed the original problem. I still have basically a over x minus 1, because of course this bracket would cancel with the squared term here, and I have my b over the x minus 1 all squared. I'll label that equation 1. Now as the denominators are the same either side of the equation, in other words the left hand side is divided by x minus 1 squared, and now so is the right hand side, I can simply now equate the numerators left and right hand side. So my equation now becomes 3x plus 7 on the left hand side is equal to the a in brackets x minus 1 plus the b, and I've called that equation 2. I would encourage you just to take a moment to understand how we've arrived at equation 1 with the common denominator on the right hand side. Example 2 continued. We're now going to determine constants A and B. Firstly, method 1, I'm going to use the cover-up rule to find constant B. We can use the cover-up rule to find the highest power of a repeated linear factor only. So we'll find constant B in this particular case. Just repeated this term from the previous slide for convenience. Applying the cover-up rule, we consider the denominator and decide what value of x we need to make the denominator become 0. Obviously the value of x we need here is 1. And then we simply cover up that term and put the value of x in the numerator and solve the resulting equation. So putting the value of 1 in the numerator for x, the value of b becomes 3 multiplied by 1 plus 7, so b is equal to 10 in this case. Method 2, the comparing coefficients method, will be used to find the constant a value. I've repeated the equation here from the previous slide for convenience. So I'm going to compare coefficients of the x terms. So on the left hand side of the equation the coefficient is 3 associated with the x term. There's my 3. And on the right hand side of equation 2 the coefficient associated with the x term is a. I've got ax. So I've put a on the right hand side. So obviously a is equal to 3 in this case. I can now rewrite my partial fractions. On the left hand side 3x plus 7 divided by x minus 1 all squared, and that's now shown to be equal to 3 upon x minus 1, where 3 is the a, and we add to that 10 over x minus 1 all squared, where the 10 was the b constant. Obviously we're actually integrating, so the left hand side is actually integrated with respect to x, so we do the same thing on the right hand side, but notice for the first term I've taken the constant 3 outside of the integral sign. So I've got 3 multiplied by the integral of 1 divided by x minus 1 with respect to x, and I've also taken the constant 10 outside the integral sign for the second partial fraction. So it's plus 10 multiplied by the integral of 1 divided by x minus 1 all squared with respect to x. On the following slide we undertake the integration process. Example 2 continued. Note that the first integral, the 3 multiplied by the integral of 1 divided by x minus 1 with respect to x, is of standard form. So if the numerator is the first differential of the denominator, the solution is ln of the magnitude of the function of x plus the constant integration c. So in this case, differentiating the denominator, the x minus 1 with respect to x, that becomes 1, and that's what we have in the numerator. So we can simply write our solution down there as 3 multiplied by the ln of x minus 1, which is shown here. Our next integral on the previous slide was 10 multiplied by the integral of 1 upon x minus 1 all squared with respect to x. Now this is not in standard form. So we're going to try the substitution method here. This is the method we looked at in a previous presentation. So for the substitution process, we let u in this case equals to x minus 1, the bracketed term. We differentiate u with respect to x, so du by dx is equal to 1. Differentiating x minus 1 becomes 1. And rearranging dx is equal to du. Again, we can clearly see our numerator is lower degree than the denominator. So now 10 multiplied by the integral of 1 divided by x minus 1 all squared with respect to x could be written as 10 multiplied by the integral of u to the negative 2 with respect to u. Notice here that the x minus 1 has been replaced by the u, and I brought the bracketed term to the top line. So that's why I can write the u to the negative 2 shown here on the top line. I've also replaced the dx shown here with the du shown here, and that's from this expression here. You notice now we've made the integral into standard form. The u to the negative 2 is of the form x to the n, where in this case the x is the u and the n is negative 2. So we can integrate that function using standard tables. So now integrating u to the negative 2 with respect to du becomes 10 multiplied by u to the negative 1 over negative 1. That's using the standard form of ax to the n and integrating. I did my constancy of integration there. Here we just simply back substituted for u, so u becomes x minus 1 to the power of negative 1 multiplied by 10 divided by negative 1. On the last line, I've simply put the bracket term below the line, in other words, accounting for the negative index here, and I've written that as negative 10 divided by x minus 1, and my constant equation is 4. So our final solution for the integral of 3x plus 7 divided by x minus 1 all squared with respect to x is 3 multiplied by ln x minus 1 from above, and now subtract 10 divided by x minus 1 plus the 3. I'd encourage you to stop the presentation and think that slide through carefully, being aware of the standard form we use and the substitution methods to solve that problem. As I said before, there are presentations on integration using standard form and integration using substitutions available. Here are some tutorial questions related to repeated linear factors. In question 5, we're asked to solve the integral of 5x squared minus 2x minus 19 divided by, in the denominator, the x plus 3 in a bracket multiplied by x minus 1 all squared in a bracket. And we're integrating with respect to x. What you notice in the denominator there, we've got a linear factor, which is this term here, and a repeated linear factor, this term here. In this case, the numerator is of lower order than denominator. We have x squared in the numerator, and if we expanded the brackets fully, in the denominator we'd have x cubed, and the denominator is obviously already factorised. The answer is stated here on the right hand side. In question 6, we're asked to evaluate the integral of 3x squared plus 16x plus 15 all divided by x plus 3 all cubed with respect to x, but between the limits of negative 2 and 1. Again, the numerator you'll see is lower order than denominator, numerator is x squared, denominator is x cubed, and the denominator is already factorised. Answer given on the right hand side, this is a definite integral, so the final answer is a numerical value. I would encourage you to stop the presentation and undertake these two questions, but the full work solutions are shown on the following slides. Question 5, we're asked to solve the integral of 5x squared minus 2x minus 19 all divided by brackets x plus 3 multiplied by brackets x minus 1 all squared with respect to x. As before, we're going to consider the partial fractions, first of all, before we consider the integration process. As we can clearly see, the numerator is lower order than denominator. Numerator is x squared and denominator is x cubed, so no need for polynomial division in this particular case. Firstly, the linear factor, the x plus 3. In terms of partial fractions, that would be a over x plus 3. Next we have the repeated linear factor, because we've got the squared outside of the bracket, so x minus 1 is our repeated linear factor, so that's written as b over x minus 1 plus c over x minus 1 all squared. I've called that equation 1. So as always, we've got to solve for the a, b and c constants. Now making a common denominator of both sides of the equation, on the left hand side the common denominator is x plus 3 multiplied by x minus 1 all squared, and now that's the same common denominator on the right hand side. But notice how we have to factor up the a, b and c constants appropriately. So constant a in this case is multiplied by the x minus 1 all squared, and note that the x minus 1 all squared term on the top line cancels with the x minus 1 all squared term on the bottom line, so we still have a over x plus 3, so that's okay. The b term is multiplied by x minus 1 in brackets multiplied by x plus 3 in brackets. And again, if you think that through, the x minus 1 on the top line cancels with the squared term on the bottom line for the x minus 1 bracket, and the x plus 3 bracket cancels with the x plus 3 bracket to leave us again b over x minus 1, which is what we have up here. And finally we have plus c multiplied by x plus 3 in brackets. Again, thinking of cancelling, the x plus 3 and the bottom line cancels the x plus 3 in the top line to leave us c over x minus 1 squared, and that's what we have in this third term here. I would encourage you to stop the presentation and take a moment to understand how we've arrived at this right hand side of the equation. What you must be careful of when you're using the common denominator on the right hand side of the equation is that you do not affect the original equation 1 shown above. As I've shown by cancelling out the brackets top and bottom, I have not. So once the denominator is the same on both sides of the equation, I can simply equate the numerators. And that's what's been done on this next line. All that's happened on the final line is I've expanded the x minus 1 squared bracket to produce x squared minus 2x plus 1, and I've expanded the x minus 1 multiplied by the x plus 3 bracket to produce the x squared plus 2x plus 9 in the bracket. I just expanded the brackets for the first two terms to help with the equating coefficient method we're going to use on the following slide, and that equation is labelled as 2. Question 5 continued. I just repeated equation 2 for convenience we'll be using in a moment. Now we've got to determine the constants A, B and C. I'm going to use the covariate rule to find constant A and constant C. Constant A is a linear factor, and we can always use the covariate rule to find linear factors, and constant C is the highest power of a repeated linear factor, so I can use it to find constant C in this case. So using the covariate rule, we simply say what value do we make x to make this bracket here become 0. Well, x will have to be negative 3 in this case. We then cover up the x plus 3 bracket, and we put the value of negative 3 wherever we see an x in the remaining equation. So in this case it will be 5 multiplied by negative 3 squared minus 2 multiplied by negative 3 minus 19, all divided by negative 3 minus 1 all squared. Evaluating, A is 2. Consider the next bracket. What do we need to make x to make this bracket become 0? Well, x needs to be value of 1. So again, applying the covariate rule, we simply cover up this bracket and we put the value of 1 wherever we see an x in the remaining expression. So in this case, C will equal to 5 multiplied by 1 squared minus 2 multiplied by 1 minus 19, all divided by 1 plus 3. That evaluates to negative 4. So now we have constants A, which is 2, and constant C, which is negative 4, both found from the covariate rule. I will need to use the comparing coefficients method to find the constant B in this case, but that's relatively easy now because I have 2 of the 3 unknown constants already found. So as reference to equation 2 shown above in this line here, I'm going to equate coefficients of the x squared term. So on the left hand side, my coefficient associated with the x squared term is 5, so 5 on the left hand side, and on the right hand side I have an A and a B coefficient associated with the x squared term. If we expand the brackets we get ax squared plus bx squared, so on the right hand side I have A plus B. From the covariate rule above we already know that A is equal to 2, so the equation becomes 5 is equal to 2 plus B, so rearranging, and B is equal to 3. So now we have our 3 constants. So our integral of 5x squared minus 2x minus 19 divided by the x plus 3 multiplied by the x minus 1 all squared can be now written in partial fractions form as 2, the A, over x plus 3, plus 3, the B, over x minus 1, minus 4, the C, over x minus 1 all squared. So we've moved from a situation where we find it difficult to integrate the compound fraction, but we will see relatively easy to integrate the partial fractions. The integration is performed on the following slide. Question 5 continued. So now we're integrating the left hand side of the equation with respect to x. So on the right hand side we've got the integral of 2 divided by x plus 3 plus 3 divided by x minus 1 minus 4 divided by x minus 1 all squared. Notice that the first and second integrals are standard form. We can use the function dash x over the function of x standard form in our integral tables. That integrates to ln of the magnitude of the function of x. So if we differentiate x plus 3, that becomes 1. So if you think of having a 1 on the top line here, brackets, then the standard solution for that will be 2 multiplied by the ln x plus 3. For the second integral we've got a very similar format. We have 3 divided by x minus 1. Again, if you differentiate the denominator, the x minus 1 differentiated becomes 1. And for our second integral, if we differentiate x minus 1 respect to x, we get 1. Again, thinking of having 1 on the top line. Then we can write our second integral down as plus 3 multiplied by ln x minus 1. For the final integral, the minus the 4 over the x minus 1 all squared is not standard form. That would require substitution, which we looked at in the previous example. In this case, we would let the u is equal to x minus 1. We would differentiate the u respect to x, so we get du by dx is equal to 1, so du is equal to dx in this case again, and we will substitute for the u and the dx in the integral. That would make it into standard form of ax to the n, as we saw in the previous slide, and the solution would then be written as plus 4 over x minus 1, and plus my c for the constant integration. I would encourage you to stop the presentation here and just think through the integration process we've undertaken using the standard form, and the substitution method is the same as that used in example 2 on the previous slide. Question 6 solution, we're asked to integrate 3x squared plus 16x plus 15 divided by the x plus 3 all cubed with respect to x between limits of negative 2 and 1. Again, we can clearly see our numerator is lower degree than the denominator, and the denominator is already factorised into a bracket. So again, considering the partial fraction first, we've obviously got a repeated linear factor. We've got the cube term outside of the bracket. So from our table on the previous slide, this compound fraction we've written as, in partial fractions, a over x plus 3 plus b over x plus 3 squared plus c over x plus 3 cubed. Call that equation 1. So again, finding the common denominator on both sides of the equation, we want x plus 3 all cubed on both sides of the equation. Notice we have to factor up the a constant by x plus 3 squared. So again, thinking of cancelling down, the x plus 3 all squared term cancels with the cube term here to leave us with a over x plus 3, which is what we have in equation 1 above. Now we multiply the b term by the x plus 3, because again, think of cancelling down, the x plus 3 cancels with the cubed and the denominator to leave the squared term. That's what we have here, the x plus 3 squared. And finally, we simply have plus c over the x plus 3 all cubed, which of course is what we have here in equation 1. So now we can equate the numerators. So on the left hand side, 3x squared plus 16x plus 15 is equal to the a in brackets x plus 3 all squared plus the b multiplied by x plus 3 plus the c constant. Put that equation 2 here. And the only difference with equation 3 is I've expanded the x plus 3 squared bracket to produce the x squared plus 6x plus 9. And again, I've just undertaken that to help with the comparing coefficients method on the following slide. Call that equation 3 in this case. Question 6 continued. Just repeated equation 3 from the previous slide for convenience. We're now going to find the constants a, b and c, but I can only use the covariant rule in this case to find constant c. That's the highest power of the repeated linear factors. Again, using the covariant rule, we need to decide what value of x we need to make the denominator become 0. In this case, x equals to negative 3. We then cover up the bracketed term, and we put the value of negative 3 wherever we see an x in the resulting equation. So in this case, c is equal to 3 multiplied by x squared, so that's 3 multiplied by negative 3 squared, plus 16 multiplied by x, so that's 16 multiplied by negative 3, plus the 15. Evaluating, c is equal to negative 6. Just be careful there, negative 3 squared of course is positive 9. We need to use comparing coefficients method to find the constants a and b. So, referring to equation 3 above here, comparing coefficients of the x squared terms, on the left hand side we have 3 as the coefficient associated with the x squared term, and on the right hand side we have a as the coefficient associated with the x squared term. So obviously a is equal to 3 in this case. Finally, comparing coefficients of the x terms, on the left hand side positive 16 is associated with the x term, so 16 on the left hand side, and on the right hand side we have 6a associated with the x term and also the positive b. So right hand side 6a plus b. We've already found the value of a, it's 3, shown above here, so we can simply evaluate now for b, and b is equal to -2 in this case. I'll let you work through the evaluation of the arithmetic yourself. So our original compound fraction of 3x squared plus 16x plus 15 divided by x plus 3 all cubed can now be written in partial fractions form as 3 divided by x plus 3 minus 2 divided by x plus 3 squared minus 6 divided by x plus 3 all cubed. So now we've changed our compound fraction into partial fractions. We will undertake the integration process on the following slide. Question 6 continued. So now we've got the integral of the 3x squared plus 16x minus 15 divided by x plus 3 all cubed with respect to x between limits of -2 and 1. And we've shown that that can be now written in partial fractions form as the integral of 3 divided by x plus 3 minus 2 divided by x plus 3 all squared minus 6 divided by x plus 3 all cubed with respect to x, again between limits of -2 and 1. Notice that the first integral on the right hand side is of standard form or standard tables, but we need to use substitution to solve for the second and third integrals. The substitution will be u is equal to x minus 3. So letting u is equal to x minus 3, then differentiating both sides, du by dx is equal to 1, therefore in this case dx is equal to du. So considering the second integral above, we've got -2 multiplied by the integral of 1 divided by x plus 3 all squared. Substituting for u, bringing the u term to the top line and changing the dx to du, we've now got to solve -2 multiplied by the integral of u to the -2 with respect to u, which is all standard forms from our tables. That's the ax to the n format, which integrates to ax to the n plus 1 over n plus 1. I'll let you undertake the integration process using the standard form in the tables, and you should find that becomes 2 over x minus 3. A very similar approach taken for the third integral. We've got -6 multiplied by the integral of 1 divided by x plus 3 all cubed with respect to x. Again, replacing the x plus 3 with u, bringing the u term to the top line and changing the dx to du. We write now -6 multiplied by the integral of u to the -3 with respect to u. Again, that's to the form ax to the n. Integrating as above, you will find that becomes 3 over x minus 3 all squared. So that's the integration process completed. We now just need to impose the limits, which we'll do on the following slide. Question 6 continued. So from the previous slide, our integral on the right hand side would now be 3 multiplied by the ln of x plus 3, that's the standard form in our tables, plus 2 divided by x plus 3, plus 3 divided by x plus 3 all squared, and we're integrating between limits of -2 and 1. All I've done here with this term is apply the third law of logarithms. I brought the 3 power to the back of the brackets. That's the third law of logarithms applied. All I'm going to now is impose the limits. So our upper limit is 1, that goes in first. So this will now be ln of x plus 3, so that's 1 plus 3, plus 2 divided by x plus 3, so that's 2 divided by 1 plus 3, plus 3 divided by x plus 3 all squared, so that's 3 divided by 1 plus 3 all squared. And impose my lower limit of -2 in this case. The same thing applies. We put the -2 wherever we see an x in the above equation. I will let you undertake the evaluation here. Just be careful with your directed numbers. You should find the final answer is -0.15362. Here are a couple of problems I will leave you with. These are indefinite integrals. In question 1, we're asked to integrate 4x minus 3 divided by x plus 1 all squared with respect to x. The answer is shown in the square brackets. In question 2, we're asked to integrate 5x squared minus 30x plus 44 all divided by x minus 2 all cubed. And again, the answer is shown in the square brackets. And some further problems here. Question 3, we're asked to integrate x squared plus 7x plus 3 divided by x squared multiplied by x plus 3 with respect to x between limits of 1 and 2. Answer shown, square bracket on the right hand side. Be careful there, in the denominator you have a repeated linear factor and a linear factor. And in question 4 we're asked to integrate 18 plus 21x minus x squared divided by x minus 5 multiplied by x plus 2 all squared with respect to x between the limits of 6 and 7. And again, in the denominator you have a linear factor and a repeated linear factor. Answer shown in the square brackets. I would encourage you to stop the presentation and attempt these problems. Here's the bibliography used to help generate the presentation and excellent engineering textbooks for technician engineers. I hope this presentation has been of interest to you, and thank you for viewing.